ECT2000 was designed to follow and locate short and open circuits without unnecessarily removing molding, panels, and carpet just to expose the circuit. The smart transmitter has been designed to inject a signal down your circuit. It has a 20-foot power lead and a green signal lead. It also has an open circuit indicator, short grounded circuit indicator, a tone on-off button, and a speaker. In the accessories, you have a blade probe. It's great for fuse terminals and relay terminals. We also have bulb adapters, the wedge-type bulb, and the double terminal, such as the 1157 bulb sockets. And the single-terminal bayonet-style adapter. Bulb adapters are great for connecting the signal to the bulb side of the circuit. A wire-piercing probe, and the back probe. We also have the alligator clip and the universal wire that allows you to solder on any kind of connector you could possibly use. The smart receiver picks up the transmitted signal that the transmitter is sending down the circuit. It picks it up by holding the open and short pickup parallel to your wire. It has a power sensitivity lock button. It has a speaker. It has a direction to short indicators which show you the direction to the short or ground. It has an open circuit indicator which illuminates when the receiver is detecting an open circuit signal. It also has a wire harness probe. It allows you to get into a wire harness that may have a signal that's shielded deep down inside of it. To turn on the receiver, just press the power sensitivity lock button. Here we have a demonstration circuit. We have a positive wire going through the fuse, going into a parallel circuit, going through 3 switches, 3 loads, and back to the negative side of the battery. Right down here, we have a short circuit. We're going to short this demonstration circuit out and see what happens. The first indication of a short circuit is the fact that the circuit doesn't work. To begin looking for the problem, you start at the fuse box itself. Find the bad fuse, remove it, and connect the blade probe adapter to the shorted terminal. Connect the transmitter's power lead to the battery, red clip to positive, black clip to negative. The signal lead is open, so the open circuit indicator is on, and the tone default is off. Connect the signal lead to the blade probe adapter. The short grounded tone is now alerting us that the signal lead, which was open, is now seeing a grounded circuit. To turn the tone off, just press the tone on-off button. The 100 milliamp grounded circuit signal is now transmitting from the circuit that will lead you to the short. Since electricity travels the path of least resistance back to the negative side of the battery, the majority of the short grounded circuit signal is also leading you down to the short. Take the receiver and turn it on. When you first turn on the receiver, it's in pulse mode. The closer you are to the circuit, the more rapid the pulse. The farther away you lift the receiver, the less rapid the pulse becomes. Holding the receiver parallel to your circuit in this direction or flip it in this direction, the direction indicator shows you the direction to the short or ground. Now, we don't advocate tracing the circuit in pulse mode. We'd recommend that you lock the reception sensitivity and then trace the circuit. The reason why we want to lock the reception sensitivity is because these parallel circuits are transmitting signals also that we do not want to trace. We want to ignore those signals. So to do that, hold the receiver close to the strong transmitting signal, press the power sensitivity lock button. Now the weaker signals are ignored. You can now follow the strong grounded circuit signal toward the direction indicators until you lose the signal. Now, turn the smart receivers because maybe the wire took a turn on you. Follow the signal until you lose it again. It's here where you might want to take a closer look at your circuit, so remove whatever's in your way. The next point we're going to cover is tracing a grounded circuit that is not shorted. Here we have the signal lead connected to the fuse terminal of a parallel circuit with 3 branches. Let's turn on the smart receiver. We need to understand that since this parallel circuit is not shorted, it will have signals of equal strength along each branch. This can make it very confusing to have signals transmitting down circuits you do not want to trace. Let's say you want to trace the middle circuit and not be confused by the other branches. You have to isolate the circuit you're tracing and connect the signal lead exclusively up to it. Take the smart receiver and lock in the sensitivity. The other branches are now free of signals, allowing you to stay on your circuit. There can be some great advantages to not only isolate the circuit you're tracing, but it can be equally important to remove the load or loads of the circuit. Here, we isolated the shorted circuit, but we have the load still in place. If we were to somehow pull the shorted wire away from the chassis ground, you'd never know it. But when you remove the load in the circuit, you can be instantly alerted by the smart receiver's toggle tone feature. A common occurrence inside a wire harness is that you have a positive wire that flows one way through a load and then back the other way through a ground wire. If you have a short circuit inside the wire harness, as we have in this example circuit here, they can cancel each other, and the signal strength is considerably reduced to the point where you lose the signal. A simple trick here is to pull each wire out of the harness just enough to separate it from the others so that you can detect the signal. As you hold the wires away from the other wires, the signal canceling effect is removed, and the signal strength will increase in that portion of each individual wire. Take note of the direction indicator of the smart receiver and observe if the other wire indicates the opposite direction. If it does, you can now assume that both wires are in the same circuit. Trace both wires as a pair along the harness until you find the problem. Let's look at this new circuit scenario. We disconnected all grounds at the end of our circuit. The middle switch is open to represent a break in the circuit that we need to find. We're injecting the open circuit signal into the main circuit that feeds all these open branches. Let's turn on the receiver and hold it over our problem circuit about 3 inches away and lock the reception sensitivity. As you can see, the problem here is that we're receiving signals from all 3 branches. Remember the main rule. You have to isolate the circuit you want to trace away from the other branches. Let's separate our circuit away from the other branches and connect the signal lead exclusively up to the circuit we want to trace. Now that our circuit is isolated, we no longer have misleading signals from the other circuits. We can now concentrate on our problem circuit. Follow the open circuit signal until you lose the signal. We're going to close this switch now. Now continue to trace the open circuit signal to find out why it's still open. Here it is. Now let's go ahead and plug in the end of the wire. Now suddenly we're receiving a tone from the smart transmitter. This tells us that our circuit has now made contact with ground. To toggle the tone off, just press the tone on-off button. When tracing open circuit signals inside the vehicle, there's a few things you need to know. First, the open circuit signal will transmit through non-conductive material, such as dry carpet, plastic panels, and this piece of wood. But the open circuit signal is easily shielded by conductive material, such as wet carpet and metal. When you're working on a vehicle and you come across a conductive shield, check to see if the circuit passes through it and has an exit point. If you find that the open circuit signal has an exit point, you can continue on. If you find that the open circuit signal has an exit point, you can continue on. If you don't find the open circuit signal after the exit point of the shield, you'll have to remove the shield and then examine the circuit closer. There could be some cases where you have to trace a wire harness, or maybe some wires removed from the vehicle's electrical system and laid out on the bench. You need to be aware that the open circuit signals will capacitive couple into neighboring floating wires. For instance, here we have a wire harness with 6 wires going through it. The switch we left open to represent a problem break in the wire that we need to find. We have isolated the circuit we want to trace, and the green signal lead is connected exclusively to it. The transmitter is now injecting an open circuit signal into our problem circuit. Now, pay close attention here. Let's turn on the smart receiver and detect the open circuit signal. Now, lock the reception sensitivity by pressing the power sensitivity lock button. As we trace the wire, we pass right over the open switch, and the open circuit signal continues to transmit along the circuit way past the break. The open circuit signal is capacitive coupling into its neighboring floating wires, and they're transmitting open circuit signals too. This condition makes it difficult to detect the break in our circuit. There are a couple of solutions to this problem. First, we can connect the neighboring floating wires to a positive voltage. If you were diagnosing the vehicle, you could solve this coupling problem pretty easily by turning the ignition key to the on position. Sometimes you can just turn the switches that go to the neighboring circuits on, and this will eliminate capacitive coupling. In this case here, I'm going to physically connect a positive voltage to all neighboring floating wires. Now let's trace the circuit again. The smart receiver now stops at the open switch. Here's a little tip. As you get close to the break in the circuit, try wiggling or flexing the wires to see if you can get it to make contact. Just like we're simulating by flipping this switch here. If it makes contact with a circuit to ground, you'll be instantly alerted by the smart transmitter's tone. This simple technique is called a wiggle test. It's important to understand that floating parallel wires that are capacitive coupling are weaker than the signal that is connected directly to the transmitter signal lead. You can easily detect the difference between a weaker and a stronger signal by observing the distance of the circuit and the smart receiver at the moment of detection. In our circuit, we're injecting the open circuit signal exclusively into the wire that's leading to the open switch. The parallel floating wires are all capacitive coupling and transmitting open circuit signals along them. As we trace them, we pass right over the open switch. Let's do something different now. Slowly lower the receiver onto the main circuit that has the signal lead connected to it. As you can see, the receiver detects the open circuit signal about 2 inches away. Now, keep the receiver at this distance and then trace the circuit. It's here at the open switch where we lose the signal. By holding the smart receiver at a constant distance from the transmitting circuit while you're tracing is the recommended way to keep you on track, as well as knowing a weak signal from a strong signal. In this example, we've got a red wire wrapped around a yellow wire. The red wire is cut right here, and we're injecting a signal into the red wire with the transmitter's signal lead. The yellow wire is isolated from the red wire, however, it is floating, meaning it's not connected to ground or positive. And of course, as we learned earlier, it is capacitive coupling with the red wire that is transmitting the open circuit signal. The receiver uses the whole area from the tip of the wire harness probe to the bottom of the housing as a pickup for the open circuit signal. Remember to hold the distance between the receiver and the circuit as you trace it out. Here, the strong signal is being detected about 4 inches away. As you can see, by holding it about 4 inches away, as you trace the circuit, the signal stops right when you pass over the cut in the wire. I like to gauge the reception distance often so I know we're on the right circuit. So if I come across another wire that requires me to get closer than 4 inches before the signal detection, I know instantly that it's a weak signal and I need to avoid following this wire. We need to stay on the wire that detects the signal about 4 inches away. One of the best tools that I use that complements the ECT2000 in tracing open circuit signals is the Power Probe 3. It keeps me on track because it detects the open circuit signal by direct contact of its tip to the open circuit signal's lead. This is a positive indication that you're on the correct circuit. We didn't intend this video to be a training tool for the Power Probe 3, but since we're on the subject of using it for open circuit signals, we'll touch briefly on a few important details. The Power Probe 3 will detect your open circuit signal because it has an invaluable feature built into its Power Probe mode. It has the ability to pick up circuit noise or signals, and you can hear them through the speaker. At the same time, it'll give you a peak-to-peak reading on the display. Some may know this peak-to-peak term as min-max. Just for your information, the min-max reading of the transmitter's open circuit signal is about 7.2 or 7.3 volts peak-to-peak. So therefore, the Power Probe should have its voltage level threshold set at 5 volts. Now let's get back to our open circuit that's capacitive coupling. Contact the tip of the Power Probe 3 to the signal lead. Now to the red wire that is cut on this side. And now contact the other side. As you can see, this is how you can determine a direct signal from a capacitive coupled signal that is weaker. The Power Probe is also great for verifying a short circuit. Just connect it to the vehicle's battery. When you press the power switch forward, it conducts a positive battery voltage straight to the tip. This means that you can apply power to electrical components and circuits to see if they work. When you apply power to a shorted circuit with the Power Probe, it's the same as shorting out the Power Probe itself. Since the Power Probe is short circuit protected, it will trip its circuit breaker before any damage can be done to it. Here's how to verify a short circuit using the Power Probe without tripping its circuit breaker. You contact the circuit with the Power Probe's tip. The green LED shows continuity to ground. Now, quickly press and release the power button. Did you see how the LEDs flickered off at that instant? That's because you had driven a voltage into a short to ground. Let's do it one more time. This circuit shows that when the LEDs go out at the instant you press the power button, you have verified a short circuit to ground. Let's fix the short and verify it again. The polarity change of the indicators show that you're now contacting a circuit that is not shorted to ground. Thank you for taking the time to familiarize yourself with the ECT2000. Review this DVD as often as you like. For more information, go to our website at www.powerprobe.com.